Everyone, welcome to Coffee with Caleffi. So we are doing an Ask Caleffi version of this webinar today. So we're going to have our tech support team, Matt and Ryan, join us, and we'll go through a topic that has been evolving, I would say, over the last 10 years in the industry as more digital mixing valves are coming onto the market. Where do they fit? So one of the ways that I like to kind of, maybe the thesis statement for this webinar is an expression that I love: the customer is always right, comma, in terms of taste, which I guess is the original thing there, that the customer is not always right as far as they may technically be wrong about something, and that's okay. And we can, like, as trainers, as industry professionals, we can figure out a better way to explain things. But the customer is always right in terms of taste. So if a customer wants to wear Croc cowboy boots to their wedding, maybe that's not for me, but they are correct that if that's their taste, they should do that on their special wedding day. And in the same sense, for the digital and thermostatic mixing valves, there's no wrong choice here. It's really looking at the job criteria and figuring out, for this project, is digital or thermostatic a good fit? They both absolutely will do the job. It's just kind of a matter of taste, is which one is going to be the right one for this day. So that's kind of what we're up to with this topic. We'll get much more into the details to figure out if it's a thermostatic or a digital that you would lead with in that particular job, or to know how and why. So we'll go through some of the housekeeping slides here. If you're having issues with the audio, I would just log back out and log back in. If you want a copy of the presentation today, I did something a little bit different that you should see on your GoToWebinar interface, like a little paper with a paper clip on it. That's handouts, and you'll see the presentation there. So if you want to grab it while we're in the webinar, you can do that. And if not, hit yes in the post-webinar survey, and we'll send you an email after the fact with that. We'll also have this up on YouTube. I'll put it up today. And then we have our whole library of Coffee with Caleffi on YouTube as well, if you want to send a recording of the presentation to a colleague or someone who can't make it today. That's the best place to do that. Depending on your jurisdiction, we will send you a certificate of attendance, and if you can submit that for continuing education in your area, go for it. We'll have the date and all the details that they're usually looking for, learning objectives and things like that, if you attend most of the webinar today. Then Hydronic 36 is in the final approval stages. We send this to the whole team in Caleffi North America, and then also Caleffi Italy, to do one more proofread, and then we'll have the PDF version of this and start sending those in the mail shortly. Then next month, we're going to have a follow-up to the June webinar. So we had the IAPMO team talk about the water demand calculator and some of the background of the tool and how they got to this starting point. We had some feedback from the webinar that, like, great, show us how to use it. Let's go through a couple project examples. We got that from a handful of people. So the IAPMO team will be back to actually do some calculations in the software to show how that tool is useful, and something that we're really excited about industry-wide, and we'll talk about it a little bit later in this presentation as well. So come back next month, that'll be a good one. Today, we've got Matt DeLuca and Ryan Kandler are joining us from our tech support team. So these guys are the two people that you will hear talking when you call Caleffi if you've got a technical question, or if you reach out to our email address for the tech support team. These are the two first responders there. So they're getting calls from everyone from a homeowner through consulting engineers about projects, how to select things, how to fix things, and they really have a good pulse for this conversation. So we thought they'd be the perfect experts to tell us a little bit more of the background for what can happen, what should happen, and how to make those decisions. So welcome, Matt and Ryan, and we'll kind of get started with the first few slides here, and we'll just kind of pass the microphone back and forth as we go through. So one of the things that we wanted to start with, we've been beginning the presentation with some sort of industry shout out. So we wanted to do a PHCC Educational Foundation shout out here. They have this GROW scholarship that is a quarterly thing that we've got the link right there that you can sign up for this. And it's kind of a cool way to support people that are in the PHCC world that are trying to move people further along in the industry. And I don't know if either of you guys have something to add here about PHCC, but yeah.
Yeah, I was looking into it. They've got 65 scholarships that they're going to be handing out this year. They're working on those applications right now, so it's actually closed for the year, but they do accept applications year round. So If you're looking to get into the plumbing, heating, cooling industry, definitely something to look into.
And these are nice too, because they're not so specific, like you must go to Harvard and work on a 4-year degree. It's like, that's great if that's your circumstance, but it's also a lot more flexible with just kind of moving forward in the PHCC world with that type of education. So take a look at that. And then another shout out we wanted to give a couple people in the kind of extended Caleffi world that were named in the Plumbing and Mechanical Contractor magazine. They do once a year the Next Gen All Stars. So Nikita Patel is an ASPE board member. So we're an affiliate ASPE company, and she's the Young Professionals chair. So she's a cool person in the industry, and we're happy to see her make the list. Jasmeet Singh is one of our reps up in Equipco. He's a technical sales specialist in the Ontario network, and is a really great trainer in his own right. And then Ali Vandale is Caleffi's business analyst in North America. And she's the one who goes through all the data of Coffee with Caleffi. So she's doing the hard work behind the scenes to make sure everything runs smoothly there. So congrats to those three, and everybody on the list outside of that who's not circled in yellow are also happy to see them on there as well. So today, what we're going to talk about is to get a better idea for what the project goals are. They will be different for every project. The high rise in New York City versus your neighbor's condo retrofit or something like that. We're gonna have different criteria, and we're gonna go through what the proper way to assess that. Again, this is kind of the customer is always right in terms of taste. That's what we're gonna go through with that. Then we'll go through some options for existing systems, which may be more limiting for what your selections are. We'll talk about some sizing things, and then the commissioning piece, which could be a big make or break depending on your project. So Matt, to start, why don't we clear up some of the terminology with just different types of mixing valves? So what is a point of distribution mixing valve? What does it do?
Yeah, so excuse me, these are going to be your ASSE 1017 mixing valves. That's the standard that they are all ascribing to. And these are going to be, your main major mixing valves. That's going to be tempering a lot of fixtures, usually in a mechanical room, with or right near the water heater. And these are going to be, again, for huge applications, larger applications, more than an ASSE 1070, which is going to be your point of use mixing valve.
So would you find a 3-inch flanged point of use mixing valve?
I hope not.
Probably not. No, it's a little bit different animal. So and you can kind of continue with the point of use, but these are going to be different sizes to look at them, but they also have a different role. So how does this line up in a plumbing system?
Yeah, so these ASSE 1070, like I was saying, these are your point of use. So you're gonna find these at fixtures, and these are going to provide scald protection. So they cannot be adjusted over 120 degrees Fahrenheit. They have inlet hot and cold check valves, and they also have the internal ability to completely shut off flow. If you were to lose cold pressure, you're not going to get scalded, because that shutter inside is going to completely slam shut and avoid any kind of hazardous situation like that.
I think that one kind of misconception with these mixing valves too is you could say, I'm going to get a point of distribution mixing valve and set it to 113 degrees, which is how ours comes out of the box, with that setting. But it is not going to shut off 3-inch flow fast if you lost the cold pressure. There's a lot of inertia in that much water flow, and that's why these mixing valves, you're not going to see this bigger than like a 3/4 inch tailpiece on a point of use mixing valve, because it does need to react faster, and there's just a little bit too much to do. If you have a big point of distribution mixing valve, we'll still do that job, but if you had a sink that was 8 feet away, it's not the same animal. You would want a point of use mixing valve to make sure that nobody gets scalded. One of the things that I was, as we were putting together these slides looking at this, so in the ASSE listing, it talks about thermal shock as far as something that it does not prevent. Matt, do you want to talk about like if you went to a hotel and opened a faucet, like what is a thermal shock reaction? What does that mean?
Yeah, thermal shock can actually be, I mean, it doesn't have to be hot water. You can be, shocked or surprised at cold water. If you've got, say you're at a hotel, you're, in the shower, and mop sinks are notorious for this at all kinds of public spaces where you've got, janitors tend to put like a nice little shut-off valve on the hose connection, on that hose thread at the faucet, and then leave that hot and cold open. Well, if you do not have check valves internally or on either of those lines, you're definitely opening yourself for flow from hot to cold or vice versa, depending on how that pressure is balanced right there. So you could potentially be standing in the shower if that mop sink is right nearby and you've got cold water kind of flushing through there. Just the stun that you get from all of a sudden a 20-degree temperature drop can actually be dangerous. I mean, especially if you've got an older folk showering, where a slip and fall can actually be really disastrous potentially. That's not something that these valves will protect against. They will in fact protect against scalding though, because again they will shut off internally if that temperature gets too high.
Yeah, so they're not magical and they don't prevent the surprise of that. And like you said, that could be cold water that you react to. And if you're if you're on like stable ground on a bath mat or something like that, maybe you just pull your hand out of the way and it's not a big deal. But as you mentioned, that could be a slip and fall that's worse than the scalding. So that's something that you can you still need to be careful of in how you execute the plumbing with these systems, but something to keep an eye on, just because what we're trying to establish with these slides is kind of what they do and what they don't do with ASSE 1070 and 1017. And there are a whole bunch of other listings as far as like eye wash stations and things that we won't get into today. Okay, so Ryan, do you want to go through, if somebody called and said, next year we're going to do a new construction project, we're trying to figure out what type of mixing valve to use. Do you want to go through some of these points and let me know how you might vote one way or the other for digital versus thermostatic based on these questions?
Yeah, definitely. Data logging, the first one. It's nice to see the trends and consistencies of your temperature and what your mixing valve is doing. With the electric mixing valve, you can data log and see what your valve's producing. We did have actually a hotel that's not too far away from here in Milwaukee where the valve was installed for 18 months and everything was running perfectly until there was a time where all of a sudden they were losing hot water, but then hot water would come restore and everything was back. And it was happening every day at a consistent time. Looking back, it was 6 p.m. We could go back, see that it was 6 p.m. and go into the operator of the hotel, what's happening at 6 p.m. And here, like Matt said, janitor came in and filling up the mop bucket and they were having a crossover. Without data logging, we wouldn't really know if that was happening or not. So data logging, very important that way. Another one is remote access, being able to read the parameters and adjust a mixing valve. If it's hard to get at, a thermostatic mixing valve probably isn't the greatest thing to do. With a electric mixing valve, you can set the controller in a convenient spot and run wires to your actuator. Another one is electricity available in that mechanical room? If it's not, thermostatic actuator can save you thousands of dollars by not having an electrician come in there. Just another thing to look at. And then thermal disinfection. Is that something that you have in the building, or maybe something that you're going to do in the future? Then you're going to want that electric mixing valve to be able to control that and do that if you need to.
And that's a really good point that, or are you going to do that in the future? Because we still see in North America a pretty small percentage of our sales of digital mixing valves for, like, we're doing Legionella management with thermal disinfection today. We're going to start that, as soon as the valve's installed. We get a lot of like, well, we think that might be a good idea to have that option. And that's where I think that that's a good vote for digital in that sense, because most of the digital mixing valves that you guys are setting up are just like, hey, can we just turn this thing on to be a simple set point of 113 or whatever your number is? But you could just change the program and enable those features instead of having to like rip it out of the school and put in a different valve. So I think that that's kind of a flexibility advantage that the digital would give you there, like you were mentioning.
Yeah, definitely.
So let's go through a poll here. Let me see if I can launch this here. So I'm going to launch this and you'll start to see this come up. So this is a question for everybody. The point of distribution mixing valve is always the same pipe diameter as a properly sized mixing valve. So in this slide here, I've got 1.5 inches. Is it true or false that this would be matched to 1.5 inches properly sized mixed outlet? So I'm going to leave this open for another few seconds here. We love to see job site photos. That can be very helpful to put things into context for Matt and Ryan as they're talking to somebody on the phone about a job site. And if we see this, it gives us a little bit something to react to. So I'm going to close this poll and share the results, and then I'll read this to you guys. I don't know if you can see it. So we got 27% true, and we got 73% false. So let's kind of walk through this a little bit, and I'll show you what we're looking at here. So if we get a picture from a job site and it's this size, it may or may not be a good fit. Most of the time, we want to know the flow rate. What is the design flow rate? That's kind of how we're going to figure it out. There's no like pipe size answer to this question. If it's 10 GPM or 500 GPM, that's actually what we need to work backwards from. If we see a job site photo and it looks like this, what do you guys think? Just at like the quickest glance, do you think this is off on a good foot?
Yeah, definitely off to a good start.
Looks right on to me.
So if we hear that we're having trouble with mixing at low flows, and this is what the job site photo looks like, that can be trouble, and we're going to go through why. But in general, we do like to see the mixing valves smaller than the mixed outlet, and we'll go through like how much smaller in a couple examples here too. So let's move over to an existing system scenario. So we talked a little bit about new construction. We'll talk about an existing system. So have you guys seen or taken any of these photos of mixing valves that come back?
None of those are mine personally, but I have definitely seen very similar type, very, very calcified, mineral laden valves coming back. Those two at the bottom look like they're full of rust and calcium and debris and stuff like that. That's flushed into that smaller opening in there.
Yeah, and one of the things that we test every valve that we ship, and when we ship them, they look like shiny gold brass that doesn't have like a single fingerprint on them. And then when they come back and they look like this, that is the reality of hard water, and that will happen. Just like time and the hardness of the water and the temperature will determine if this is something that happens in the first month or not for 10 years. We don't really know. It's very regional. It can be just like how deep your well is compared to your neighbor's well could be a difference maker here. So this will eventually affect the performance of the valve. We make the products in a way that they're anti-scale polymers with the cartridge and things like that. And we'll talk more about the self-cleaning piece as well. With the digital mixing valves, the ball can rotate once a day to just wipe the scale away, kind of like the windshield wiper or like brushing your teeth every day, that you can kind of manage the scale just by having an override to say, okay, let's just do this at 3 in the morning and make sure that this isn't building up. Where a thermostatic mixing valve will eventually get to a point that there is scale kind of closing in from both sides to keep it out of its full range of motion, unless it happens to cover full hot to full cold every single day, which it generally wouldn't. You can start to see some of these effects of scale. So sometimes We get returns. I've seen these at the International Return Department. We've all seen them at the Return Department in Milwaukee, and they'll come back and they'll say something mean with Sharpie as far as like defective, does not work, and then we open it up and it looks like this. And that's okay. There's just, we need to make sure that if this is what's happening all the time, that could be another vote to move to a digital. If you're replacing, we've had some cases where replacing a 2-inch mixing valve with just a new valve body is an option, and that's an easy switch, and that's breaking 3 unions and putting a new valve in and putting it back together could be a 15-minute service call. However, that's a lot of brass in those, and it's not just a Caleffi thing, but like anybody's thermostatic mixing valve. If you're replacing the valve body every 6 months, it might be a cause to move to a digital mixing valve. Maybe less expensive to do that in some cases too. So, okay, so let's go on to a sizing example that we'll kind of work through. The Hunter's curves has been kind of the abacus of the industry for plumbing fixtures for a very long time. This is something that was developed initially in the 1940s by Dr. Roy B. Hunter. Everybody has a modified version of this, I would say, in engineering firms across the world at this point. But this was developed in a time that maybe Roy B. Hunter drove to work in that Packard. This is what a car looked like at that time. And this is also what a toilet flush looked like at that time. So all of the fixtures were using so much more water than we would now with EPA compliant fixtures that are low flow flushes and things like that. So if we were developing a plumbing system to use these fixtures, interesting side note here for people who haven't seen these, you can buy this on Home Depot right now. You can buy a toilet like this for your cool loft downtown that's been converted from an old factory or something like that, if that's the aesthetic. That would be important to know as a system designer, to know if this is going to be an 8-gallon flush or if it's going to be a 1.2 or something like that. But we need to know what fixtures we're working with, and probably not going to be this scenario. So one of the things that we've been advocating for is looking further into this IAPMA water demand calculator. They're moving initially with single family and multifamily, and they're looking at more use cases that was described in our June webinar for how to size for, I think they're working on like hospitality and some other kind of more common use cases, to plug in these numbers and get a much more modern answer to that sizing question, which I would say, if you guys can answer this first. If you got a phone call and said, hey, I just picked a mixing valve, a thermostatic, and I used the original 1940s Hunter's curve, and then you got another call at the same time and said, hey, I just sized a thermostatic mixing valve with the IAPMA water demand calculator, which one would you say is going to end up with a shorter phone call as far as troubleshooting goes?
Definitely the water demand calculator. Yeah, I mean, it's just so much more accurate. I've even seen case studies where you size it with the water demand calculator instead of Hunter's curve, and it's a drastic, like something like 70% reduction in flow. And then when you actually strap an ultrasonic flow meter on there and get some real world data, it's even below that. Like that, even the water demand calculator is oversizing at that point.
Yeah, and I think that's something that when you hear numbers like that, like 70% less, and I think that the engineering and plumbing community is like, that's like too good to be true. I don't trust that. But there's so much more data to show that this is like, even the outliers are still covered with this. Only in the extreme cases that I think that they had an example that hospitality can be tricky because some people will just leave the hot water on for 40 minutes to steam their clothes or something. That's just like, okay, well, we didn't, that's not really normal use. We do have to accommodate for that, but even that could be still wildly less than the Hunter's curve there. Okay, so Matt, why is it that like proper sizing is important for selecting a mixing valve? What's going on with this chart? And then you start there, and then I've got a follow-up question for that.
Yeah, so I mean, these valves are made to deliver a certain amount of hot water, a certain amount of mixing, to deliver at whatever that demand is per fixture. So like the point of use, the sink mixer that you're showing right there has 3 ACE compression connections. That's literally going to be installed to serve a single or sometimes 2 faucets, 2 single labs. And that's a much smaller flow rate than, for example, on the right, you've got a flanged Legio mix, I mean, they can handle hundreds and hundreds of gallons per minute for an enormous hotel or, you know, banquet center, something like that.
So if you see an ad for a mixing valve on the market and it says the works with 0 GPM minimum flow rate, is that the full story there, or what else would you look for in that case?
Yeah, if you see that statement, you should at least see a little asterisk right at the end of it too. And if you follow that asterisk down to the footnote, it's going to say with adequate recirculation or something to that effect. We're a little bit more, you know, upfront in our literature where we call it a quote unquote minimum. So that minimum flow rate, as long as that flow rate is covered by your research system, that's where that 0 comes from. So above and beyond that, you know, 0 GPM, it's taken care of.
Yeah, and that's important to note because you will see that temperature. We've got the outlet gauges for these different mixing valves, and you will see that hunt a little bit if you're below, in this example, the like 2.2 GPM. If you did not have a recirc pump or the recirc pump was turned off or something, and you have like 1 GPM of flow in that building, you would see that hunting to try and find the right temperature. But as soon as you meet that minimum, which is a lot lower with the digitals than with the thermostatic, so 4.4 versus 3.1 for 1-inch valves there. As long as you exceed that, the recirc pump should take you most of the way there, even if it slows down like an ECM pump should. That's when you're going to see that stabilize. If you have 0 GPM of flow, you can't move water over a sensor to know what to react to. So you can't get a radar reading of a car that's parked. There's no input there. Nothing has changed between those like bounces of the radar. Kind of the same thing with either the sensor that's a wet well, that's an electronic thermistor, or the like wax element inside of thermostatic mixing valve. They need to react to something. You need to have some flow for that to work. Okay.
And that's
go ahead.
That's one of the biggest tech questions that we have, is if our Legio mix isn't functioning properly, it's always that recirc, and it's just not enough flow going through that mixing valve.
And that's going to lead
to that out too is if you open up enough fixtures, say, sometimes in a larger facility, if there's a leak or something like that, a lot of times the maintenance guy will open up a ceiling tile and just start closing valves. You could wind up, with a recirc branch that's completely closed off, unbeknownst to everybody else, and all of a sudden that valve is hunting. You're not quite sure why. If you open up enough fixtures to facilitate that minimum flow, and it settles in, now you know that there's something either with the pump or somewhere else within that system that you're not getting enough flow.
Yeah, that's a good troubleshooting tip just for anything, is like write down some of the other, what time is it? Is it 4 in the morning that you're noticing this, or is it at you're having issues that in the hotel only when you're at full occupancy does it not keep up? That could be a completely different thing. That could be that the thermostatic mixing valve has scaled in a way that it can't get as much hot water out to the building as it should, or it could be undersized, which is a pretty rare one, I would say. But those are good things to know. Like what is the demand right now? Is this like at the minimum or maximum of what you would expect? And without even having engineered the building, that can be useful for troubleshooting there. Okay. Let's go through a project example to just see with one set of measurements here that we'll say that we have engineered calculations of a building that's going to need a 5 GPM minimum, 30 GPM maximum, and we want to set a pressure drop limit across the mixing valve of 10 PSI. Where does that line up here? So I'm going to go through these kind of quick and show you where they would line up with the two different products that we have. It's going to be similar with different mixing valves in the industry from other manufacturers too. This is just kind of a technology versus technology explanation here. So we'll say we have a 5 GPM minimum, got a 30 GPM maximum, which is actually just going to cross into this red shaded area, which is going to be a 10 PSI drop across the valve. So you are going to have, a 11, 12 PSI drop across the valve at that scenario. Again, it won't be that much at a lower flow rate. Just as you get more gallons per minute moving through, you're going to see the length that the shower is going to hit the back of the wall. The shower head's going to hit the back of the wall, may drop a little bit. That would be kind of hard to see for a 2 psi drop. But at the most extreme, if you went to the run out of this valve and you had a 25, 30, 50 psi drop across the mixing valve to save some money on the brass up front, you would have a lot of very weak showers in a hotel at that point, and we don't want that. So that's kind of where it would line up. In this case, you would have an 1.25 inch mixed cal plus. So that would have a minimum flow rate of a 4.4 GPM to make sure that you're not hunting at that low flow rate. So we've got 5, so we'd be in good shape there. Now, if you haven't ever seen a cross section of the thermostatic mixing valve, this is pretty common to get like an ASSE 1017 listing. You're going to have a pretty similar shape here. There's not miles in between the different manufacturers of how you make a thermostatic mixing valve. It's kind of more in the materials and the consistency and the machining and things like that. This has a C sub V of 7.6. This is the flow, the path of water going through a thermostatic mixing valve. So you have a pinch point right here because you have the hot and the cold on the left is the hot, the right is the cold. And then you have that tan shuttle in the middle that's moving up and down to give you a different ratio of hot and cold. So there's kind of a pinch point here. This is a small passageway for water to flow through a valve. Works great. This is some of the most stable technology in plumbing. This is very, very simple. We just have a wax element that's expanding and contracting to give you a different ratio there. But it is a little bit of a pinch point for a pressure drop. So let's look at the digital mixing valve and just kind of compare a couple things here. So 5 GPM minimum flow rate, 30 GPM maximum flow rate. In this case, and I used kind of an extreme example here just to make a point. We can go through how you would make your own decision here. This would line up with a 3/4 inch Legio mix, which if you saw this in a hospital, even if it were properly sized, you might think did you guys get that for free in a raffle? Why do you have some residential size mixing valve in this project? But this is how we would kind of do the math to show, no, this is the right digital mixing valve for the project. And here's kind of the major difference. The C sub V for this valve is 9.7, even at 3/4 inch, but that's the flow path through here. So that's one of the things that in a training that we like to point out is that you can look through just look into the port of a digital mixing valve and see a much different scenario than looking and seeing a bunch of different objects in the center of the thermostatic mixing valve. Again, neither of these is wrong. They will both mix water from 5 to 30 GPM in this scenario, but that's why you can go so much smaller with the Legio mix, the digital mixing valve, because it's a diverting ball essentially. Okay. We then will get a follow-up question sometimes and they'll say, okay, wait a second, you're telling me we're going to move 30 GPM through 3/4 inch pipe. That's what we're kind of saying with the easy chart here, that if you want to move 27 GPM at design flow through a 3/4 inch valve, this is the one that you would pick. What does that actually mean if we get into the velocities of the valve? So if you guys were going to go out into the field and pipe a hotel and they said we need 30 GPM, the engineer says we need 30 GPM to go out to the building, and you said, hey, we can save a lot of money if we pipe this entire building with 3/4 inch pipe, what would you expect to maybe happen in that scenario?
Get ready for leaks in the next couple of years. It'll just rot its way out. It's just the velocity and the flow is just too fast for 3/4 inch.
Yep. So what kind you would see pinhole damage?
Yeah.
What other things would you expect there?
Brittle plastic piping. There's just always defer to the manufacturer's recommendations for temperature, flow velocity, and pressure ratings.
Yeah, that's a good one too, because they're anyone with an ASSE listing for piping material, we'll be able to handle plumbing water in any reasonable expectation of the systems that we use in North America. If we're talking about a space shuttle or something crazy, then you're gonna have to look a little bit harder. That might be some sort of stainless that has a life expectancy of 48 hours or something like that. There are some industrial applications that they're repiping everything in stainless every 6 months. Just whatever they're working with, ink or Mountain Dew or whatever, is just going to be more corrosive. every piping material that carries a listing appropriate that a jurisdiction will allow it to be used in a plumbing system will work in these scenarios. You just have to figure out what their velocity speed limit is, essentially, like Matt's saying. So let's take a deeper look at this 30 GPM design scenario. So we use the easy chart up here to find, okay, 3/4 inch valve looks like it's about right, but what does that mean for velocities? So we'll take a look at the more complex chart here. We've got 27 GPM design, but what does that mean for the pressure drop? So we're somewhere between 7.5 and 10 PSI drop across that valve in this 30 number that we had, closer to 10. So if we were to use 3/4 inch pipe throughout the building, we'd be moving like 16 to 19 feet per second. That is screaming fast. You would hear that. That's moving way too fast. That's not good. We would not recommend piping the building like that. And that's why you see the sizing difference between the properly sized mixing valve, which is built for that. It's built for that velocity. It's a control device. It has either a nickel plated brass or stainless steel ball that's like, it's okay with that high velocity. But the copper pipe in this scenario would not be. So you would want to go up to 1.5 inch pipe size for the mixed outlet. So properly sized 3/4 inch valve with 1.5 inch mixed outlet in copper to stay below that 5 feet per second seems odd, but those are the properly sized devices for this scenario. So if you had somebody, Matt, call and say, I can't quite go there, I want to go with the 1 inch valve instead of going all the way down to a 3/4 inch valve, where would that, what would you notice that would be a little bit different with a 1 inch valve versus a 3/4 there? Would it still work?
Oh, it would, yeah, it would absolutely work. You would have a lower pressure drop than you would through the 3/4. And the main thing is to make sure that your recirc system is able to keep up with that minimum flow rate. So, I mean, it's only a GPM more, I mean, really in the whole scheme of things, when you're talking about a system, delivering 1.5 inch hot water out to a hotel or a large building like that, 3 GPM is nothing in something that size.
Yeah, so that you would be covered with the 1 inch. You spend a little bit more money there, but if that makes you feel comfortable, you are still covered there. Let's say, Ryan, that they said, I'm going with 1.25 inches. Would that valve ever open more than 5%?
No, that valve's going to stay basically as close to hot, as small on hot, I should say, and it won't open fully. So what you can see happening is getting lined up or gunked up with it not always opening and exercising, basically.
So we've got a couple issues there that we're still covered if we went with 1.25 inches at a 4.4 GPM minimum if we said our number was 5. So we're still hitting the minimum flow rate, which is good. So it's not going to be hunting. But if we're going to 30 GPM and this valve, comfortably will go up to 66 or even at, much higher pressure drop, 15 up to 93 GPM, we have a pretty, it's the analogy that we were using earlier was you have a pretty small steering wheel for a pretty big ship at that point, that you're going from 0 to 2% open back and forth versus the 3/4 inch valve. You kind of have the whole swing there. So it's going to be more consistent because it's really fine tuning with a lot more to work with instead of just open, close at that lowest flow rate, which, if you hear the actuator moving a lot, it could be another indication that you're oversized there. You shouldn't hear a digital mixing valve zzz, 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 back and forth. That might be an indication of oversizing there. So shout out to Cody Mack, who's watching some of the questions on the webinar today. He designed the Delta 2. This was a product that we used to sell as a rack assembly. This is a high-low mixing station. So we had a small mixing valve, a 3/4 inch mixing valve, and then a large thermostatic 1.25 inches. So Cody put this together. And then we did something really mean that we took this out of the catalog on Cody. So we're going to describe, what happened here, because this system works great. If you wanted a high-low thermostatic mixing station, we used to ship it with the Unistrut and everything in a rack assembly, so it was ready to plug in. What we found is this is a lot of brass. So this is 3/4 inch, 1.25 inch mixing valve, then 1.25 inch pressure reducing valve. Just from a material standpoint, this is a lot of brass versus, in this case, you might be able to go with a 3/4 or 1 inch digital mixing valve was just a lot more cost competitive from a material standpoint. And then even with the controller for the digital mixing valve, in our catalog, they ended up being kind of a price parity. So there were people that were using this, and then when they looked into the digital mixing valve, they started to make more of that switch. And again, both of them will work fine. The reason that we internally moved away from this is that there was just more coverage with the digital mixing valve and you added more features there. So we're going to kind of go through how you would commission these two different systems. But again, if you have one of these out in the field, you can break the unions of any of these three components if they were damaged by some debris in the system and put them back together, and they will work fine. We're going to go through how you would do that in the next few steps here. So what I'm going to do is launch another poll here. Let me get this one started. And Cody, if you're on the call, you can weigh in if you're mad about that, or if you're okay with the Delta 2 no longer being in the 25 catalog.
I only shed a few tears, but we held a little service for it and everything like that. There was shrimp cocktail and whatnot. So it's all good.
So yeah,
had quite a few questions that we've had coming in, some really good ones. I think what we'll do is I don't know if you want to do them now or if you want to wait till the end. What are you thinking there?
If you have a quick one while we've got this poll open, and then we can touch some more of them at the end.
One of the ones that came in was about point of use mixing valves providing bypass for sterilization and thermal disinfection to the end of the tap. And while our sink mixer does not do that, there are some ASSE 1070 valves that allow for bypass. And one of the things that always concerns me about that is that most codes have maximum temperature for whatever you're discharging into the sewer of 140 degrees. So you do have to be mindful of that. And if you are doing that on a larger scale, making sure you've got drain tempering going on before it ends up out in the street, and you even couple that with the fact that PVC just isn't going to like that all that much when you're shoving 140 plus degrees down the drain. But I don't know if you guys have any other thoughts on that too. I just thought it was a really interesting comment.
I think about that every time I dump a pot of pasta water into the drain. It's like, wait, who signed off on this? Do I need to test this 55 gallons of ice water before I put that into the PVC?
Right. I don't know who's enforcing it, but they're listening right now, Max. They're coming to your door, so you better be ready.
Do you guys have anything to add there? I know that from a product development standpoint, that is something that we are capable of doing. We're just kind of waiting to see if that's something that's being spec'd in more buildings, because like Cody's saying, there is a different kind of hazard presented if somebody does the override. That's exactly what that valve is supposed to prevent. We don't want somebody to be like, no, I'd like a warmer hand wash here, and they're going to pull the lever or something if they figure out how it works. What do you guys think?
Yeah, that's always been my first concern from the moment I saw that thing was, wow, we're this close to scalding. I mean, it's that valve is installed with a purpose. Obviously, I mean, it's got that thermal override for a reason as well, for thermal disinfection, which is something that's becoming more and more popular, and our Legion is set up to do. I just personally, it kind of gives me the heebie-jeebies whenever I see it.
Yeah, and I think that we'll see. I think that there's an application for it, and I understand how it would be nice to get that run out to the fixture all the way through to the sink with hot water, and that's kind of best case scenario, so you don't have potential for Legionella to be kind of hanging out in that last little bit. There are some other things that you can do to just keep the recirc line closer to the run out, so you don't have a 28-foot run out to the fixture that goes snakes through the wall or something like that, and to go with smaller pipe sizes. So I know that that's kind of an industry trend right now as to can we do 3/8 to these fixtures? Why does everything have to be 1/2 inch or 3/4 inch? Do we have more volume than we need there? Would it be better to have a smaller volume of water for that run out? And then I don't know, there's no perfect answer there, but those are some of the things that we're kind of working through internally as well. Okay, for the poll, can you properly commission a high-low thermostatic mixing station post-occupancy? We got 66% true, 34% false. So I would say that you absolutely can. My question to Ryan and Matt is like, do you want to? Is it easy? Like, what's the answer to that question?
It's hard to, because you just can't truly control that flow when you are commissioning it or trying to set up that high-low thermostatic station.
And why don't
Yeah,
we go ahead, Matt?
I was just gonna say, I mean, unless you have like, you know, that high-low serving an entire wing, and you can isolate that wing, and you can empty that wing, and you can, you know, ideally you want almost no flow conditions in order to just focus on that task at hand as you get it dialed in.
And one of the things that I was at an Ashbury event, we were talking about a hotel that they got a note on the door that's like, hey, we're going to be working on the plumbing system between 2 and 4 a.m. today. So just like know that there will be interruptions. You might not be able to take a hot shower or whatever. It was like very polite. And then of course, like people are up trying to take a shower and calling down to the front desk at 3:35 in the morning. That would be ideal, as if you could pick a time where there as few, you know, if it's a commercial building where like, yeah, there's nobody in this building after 5 p.m. on Friday. So let's do it over the weekend or something. That would be best case. You really don't want to try and do any of these steps that we'll describe at 4 p.m. in a hotel, when you just have like the occupancies all over the place. So let's go through this, and we're not going to do like every single bit of this commissioning sequence. I just wanted to have Ryan kind of give you an overview for these different steps for how we would commission a high-low thermostatic station if we installed one today.
Yeah, so what you would first want to do is you want to focus on your smaller mixing valve. So what you do is you isolate the big mixing valve and the PRV, and then you would want to go around, turn some fixtures on to get 2 GPM to flow through. And then what you would do is adjust that smaller mixing valve to 10 degrees less than your set point. So for example, like this, if your set point is 120, you'd want that smaller mixing valve to set to 110.
Then here's step 2.
Yeah, so for step 2, you basically now isolate that smaller mixing valve, and then what you're going to want to do is go around to your fixtures and ramp up that flow to 12 to 14 GPM, and then dial in the bigger mixing valve to that 120, and get that flow and make sure everything's right at that point.
Then we kind of have this for big and small, but now tell us how we like merge that so it all makes sense.
Yeah, so then you just want to keep that flow up there at, you know, that 12 to 14 GPM, and then take a look at that gauge, keep your eye on that gauge, and then adjust actually that PRV and get it set to 6 to 7 degrees lower than your set point. So, you know, for example, you're going to be looking for 113, 114 coming out.
And then that's going to kind of give you the coverage for both of those scenarios. If you had a bunch of people in a hotel opening fixtures as you're trying to do this, you just are really chasing your tail a little bit to know that like we're steady at 12 or we're steady at 2. And that's kind of what we meant with the poll. So then what's the last step here?
Yeah, so then at the last step, you know, go back and then you slow that flow down to that 2 GPM, and then adjust that smaller mixing valve to that desired outgoing temperature of 120.
Yep. And then kind of the key here is that we want the small mixing valve to do all the work until there's too much flow going through it. And in PRV terms, we're having like the pressure fall off. We're starting to notice that we're not keeping up from a pressure standpoint. And then the PRV notices the downstream pressure is low, just like you would do it for the cold inlet into your house. And so like, okay, the pressure is low, I'm going to open up a little bit, and then it engages that bigger valve. And that's, you know, absolutely technically works great. The tricky part is being able to find steady 2 GPM flow and steady 14 GPM flow to do this. And that's why pre-occupancy is always the best case scenario.
Yeah, correct.
Okay, then this is kind of on the end of the recirc line. So after the water is all the way back from the building, what we wanted to do is kind of mention a couple commissioning things here too. So when we bring the recirc line back with the thermostatic mixing valve, we want to have 2 different balancing valves here. And the way that we describe them, I've heard them, a bridge valve and different things like that. In the literature, we call it a bypass valve and then a return valve. So what we're trying to do here is essentially match the heat loss going from the mixed outlet. If we're mixing out at 113 and it's coming back at 100 in this example, none of these numbers that I use are like, you should always come up with your own numbers. That wouldn't be necessarily good, like Legionella management, to mix out at 113 just kind of for the math of this. So it's coming back at 110 degrees. We lost 3 degrees of temperature. What we want to figure out is how much of that water do we want to just go right back out to the system, and how much do we want to go back to the tank? And the adjustment of this valve, of these two valves, prevents either recirc creep, where the recirc line is increasing in temperature all the time, or recirc droop, where in periods of low occupancy, the recirc line bogs. In that scenario, we didn't have enough coming back to the cold inlet to go out. In a recirc creep scenario, we're having too much go back to the cold inlet, and we're mixing hot with hot essentially, and we can exceed our set point. So then we need to adjust this. Same thing, pre-occupancy is really the best way to do this, with only the recirc pump going. That's kind of what we want to do there to make sure that we're getting this right. If we have a bunch of fixtures on, it's going to change what that heat transfer, what the heat loss is out in the building. So pretend like this is hydronic baseboard, and we want to figure out what the delta T is here, and that's going to help us adjust it. So then on the next slide, it's kind of a manual process, but do one of you guys want to kind of describe what happens opening this like globe valve or balancing valve 1 open? What are you looking for here?
As you're opening that, okay, that bottom one that's heading back to the tank.
Yep. So
yeah,
what do you want to look at here? Let's say we have a mixed outlet temperature gauge here, and you're opening this valve. What are you kind of shooting for in this scenario? There's not like a specific like number of turns that we can recommend, but like what would you look for to stabilize here?
Basically, whatever flow rate it takes to match that temperature that you're mixing to and sending out to the field.
Yep. So if you're looking for 113 degrees out and you start to adjust it, and it with the recirc pump running for 5-10 minutes and it is 120, 125, you haven't adjusted it right. You want to open it so that you see that 113 stabilize, basically is kind of our goal here. And it's not something that can be set ahead of time. This is something that has to be done per project. You can kind of get an idea with doing some of the math, but it depends on how well the lines are insulated, and a lot of different installation considerations here too. So this is a bit of the commissioning for thermostatic mixing valves. We have this in the product literature as well. This isn't Caleffi specific. This is just kind of how to use this technology in a commercial system where you've got a central tap going back to the commercial tank here. So why don't we contrast that to the digital valve commissioning stuff? And then Matt, if you want to kind of walk us through this slide, and what are the steps you would need if somebody says, hey, I just installed a digital mixing valve. What do I need to do to make sure it's going to work right?
Yeah, so first thing you do, you plug it in, fire it up. Like you said, right out of the box, it's preset. Our Legion mix is preset to 113 degrees Fahrenheit. That's where you're going to keep it. Great. If not, you'd make that adjustment. At that point, you want to make sure that your recirculation pump is running. Ideally, again, this is with an unoccupied building, or yet to be occupied, so that you've got that minimum flow rate met, and then you can basically walk away. I mean, I walk out past Ryan, who's still tinkering with his high-low, and I go grab lunch.
Yeah, so it's just the amount of slides it took to put this in the presentation. We're talking about like a single slide here. So if you're calling, if you were calling any of the three of us on the webinar today, or anybody at Caleffi, if we're pretty solid that we're meeting that minimum flow rate, like we're in good shape to figure out the rest of the things here. There may be some programs that you want to decide, are we doing thermal disinfection or not? That's kind of a bigger conversation, but we just don't have as much to work around as the thermostatic stations. And again, not that one is better or worse. This would require you to get 24 volts to this controller and some other things that are ahead of time. Maybe the building management team, the integrator for whatever the hospital is using, that's a conversation too that's ahead of time. So this is just mechanically, what does it take to get it up and running? And that kind of leads into the next one too. And I don't know, Ryan, if you want to start with this one. We published 2 different piping diagrams for the Legio mix for the digital mixing valve. We have one if you have a big commercial tank that has a center tap for a recirc line, versus maybe this is like a light commercial application where you just have a bottom and a top port to a tank. Those are important things to know. Then what would you kind of look for next if you were going to evaluate some piping, Ryan, for a photo that came in or something like that? What are some pitfalls here?
You just want to look and make sure that you are getting consistent flow through that recirc of that digital mixing valve. We're always looking for that minimum. Sometimes we'll get pictures coming in and they only go to the cold side, and they'll have a check actually going into the tank to where it's not allowing it to go back to the cold feed of that tank. Unlike on the other picture on the left there, where you actually do have a port and they will separate it, and then you do have consistent flow coming from the hot and the cold side of that digital mixing valve.
Yeah, that's the most important part, I think, is that in this green circled area over here, we actually have 3 different check valves. So we have the recirc line coming back. We want to make sure it can get to the tank. If the port is open, the cold port is open in the mixing valve, we want that to go right back out to the building. And if it's still warm, if it left at 113 and it came back at 112, this might be full open to the cold, and just let it go back out for another lap. And only when it cools does it crack open the hot port a little bit. That's fantastic. We don't need to always engage the full volume of the tank. If the recirc line is still warm, let's just send it out for another lap and then top it up, instead of going all the way through the tank to kind of engage that whole volume and potentially stir up the stratification of the tank. So as you were describing too, if we just have, coming back to the cold inlet, if we put a check valve pointing up in this piping diagram right here, that's an easy mistake to make. And we don't want that, because we want the water coming back from the recirc line to be able to go up or down in this scenario. So if this cold port is closed because the power was out for 24 hours and we're just kind of getting the cold building up to temperature, this could be full hot. The digital mixing valve can do 100% hot or 100% cold. So we've got 100% hot going out to the building. This is fully closed. In that scenario, if you had a check valve right here, you wouldn't be able to get the water from the recirc line to go anywhere. It would be kind of a deadhead situation. We want that to go back to the tank in that scenario. And if not, if we're doing, the recirc is up to temperature, we'll just send that right back out here, and it can go up or down in that scenario. So that's a tricky one. That's why we publish both of the diagrams, because it can depend. But if you're going to troubleshoot a system and you're having issues with it, take note of where the check valves are. Double check that they're pointed in the right direction. I don't know, we're not going to name names here, but I don't know if you guys have ever had a check valve that's been installed the wrong direction. That can really screw up this type of piping for sure. So, and that's where like a dual union check valve is nice too. You can take it out and flip it over without having to repipe anything major. Okay, so then the last kind of commissioning steps, anything we didn't cover here. I don't know if you guys want to kind of cover some of these that we haven't yet, and then we'll go to the last slide and we'll do some questions. Anything else you want to mention to kind of close it out from this slide?
I mean, it's showing a picture of our pre-built mixing stations that we also offer, that actually Ryan and I build ourselves. You just they come pre-piped to that rack, hang that rack on the wall, pipe in hot, cold, mixed out, and then recirc back from the building. And there's that bottom right port is actually that recirc line back to the tank. So it's all pre-piped. You got your check valves and everything in there. Power cord, all your sensors are wired up. It's literally just hang it on the wall, plug it in, pipe it up, and you're up and running real quick. If you are going to be connecting it to a building management system, there's room on that DIN rail with controllers hanging for a gateway, and it's just coordinating with the with the comms guys and getting that all dialed in, but otherwise it can't be easier.
And there's one thing that like I've noticed in the industry, and Ryan, let me know if you've like seen this as well. The like plumber and the controls contractor and the electrician in a room together, like is there potential for some headbutting there for some like
yes, there is headbutt going on.
Yeah, so there could be
in one area.
You want the mixing valve on and working, and you have 3 different people who kind of need to be in the right place at the right time. Absolutely, again, possible. But one of the things, as mentioned, that like these guys are great at wiring these things and then get the the wire length right and plugged into the right port. So you're plugging this in like you're plugging in a phone charger can save a lot of time. So the rack station is more expensive than the valve only. It depends on your labor rate and if you're confident that that group can get the, what is it? There's like an engineering term for like the charrette or something, that like the meeting of all the trades to make sure that this is going to go smoothly. If you don't have confidence in that, that can be a reason that the rack station makes a lot of sense, and you prefabricate when possible to make sure that the hotel is back up and running really quick. We have some projects where they mount this on the wall before they even take the old valve out, and then are just kind of pressing back to the corners of this, got all the isolation valves in the right spot and are ready to go and make a short downtime to switch. So if you have other project questions, anything that you want to talk about, this is the tech support phone number, so you'll catch one of these guys, except for right now because they're in the webinar, so that's rolling to the other team members in the phone tree. And then you can also email us. So this has become helpful as well because we get job site photos and we can kind of get some more context for the project and then attach links and send things back like that. So reach out to the team. We're happy to help with your projects. And with that, I think that we'll go to some questions. So Cody, if you have any questions on the top of the pile there that would be good to address in the webinar, let us know.
Yeah. Oh my gosh. Yeah, we had quite a few good ones in here. One of the ones that came in early, they were asking about what codes require a master mixing valve or ASSE 1017 mixing valve, and I don't know if I have a great answer for that. I know in a lot of cases most codes require storing at higher temperatures for basically bacteria reasons, and the fact is you can't just be sending out 140-degree water. But I don't know if I remember specifically 1017 being called out, or if temperature control in general be between either point of distribution or point of use mixing valves. Do you guys have anything to add in on that?
No, nothing that I haven't heard of anything where it calls out like a 1017 or but like you said, it's just mostly with them storing hotter water to prevent bacteria and Legionella and stuff like that.
Yeah, here in the state of Wisconsin, at least, healthcare facilities are their own code. Basically, it's
Sure.
their own subsection of the plumbing code, and you're right. They require you to store at a higher temperature, and in order to avoid scalding, you have to mix that back down.
Yeah, and like I said, my eyes have been just scattered all over here with these questions. It's been pretty awesome. So let me see if I can find any other ones.
I'll add to that, Cody, is that regardless of what the local jurisdiction says, we don't override anybody as the manufacturer. You have to pay attention to what the inspector says. However, if you are doing any sort of thermal disinfection project where you're going to elevate those temperatures and recirc that, you must use point of use mixing valves, and that like may or may not be the case for whatever jurisdiction that you have, but just from a safety standpoint, we have to like make sure that we stress that if you're going to circulate 155-degree water, no one can feel that on their hands. So that would be something that in all good uses of thermal disinfection, you would have protection at every fixture to make sure that nobody's getting a super hot bathtub or sink, because water at 155 degrees from a thermal shock standpoint would knock you back on your feet, but also would give you a burn quick.
Yeah,
so,
good thing. We actually get that question on the tech line a lot, where people are just commissioning a Legimix, and I'm like, well, are you guys doing a disinfection program? They're like, well, I'm not really sure. And I was like, well, before you do, you have to make sure that you've got mixing valves at every single fixture that's being served by that hot line. And they're like, oh, well, then we must not be. It's like, well, yeah, you just absolutely no ifs, ands, or buts, no way around it. Have to have point of use mixing valves if you are going to be doing a disinfection program.
We did have quite a few comments, and I really appreciate you guys all hanging on for the just past the hour here. We've had quite a few comments in here about IPC requiring hot water to be temperature controlled by a device that is not the heater itself, so that, you know, whether it be point of distribution or point of use. You know, there's a couple of where they're calling out sections for IPC, but thanks, Kyle, for one of the commentary in there. That's a great little piece there. Adrian calls out there's a section in IPC calling for 1017 as well. So yeah, food for thought. Yeah.
Perfect.
Go ahead.
Okay.
Go ahead. I'm still looking through the questions here. There's like some good ones in here.
No, and I would say that that's like a judgment call thing too for installers. Like if you go to a building, this happened to my dad when I was a kid. I remember this. We went to a friend's house, and the friend's dad was like, "Oh, you're a plumber? Can you turn up my water heater?" And he was like, "I can, I won't." And it was like kind of a, I don't know if I've talked about this in Coffee with Caleffi before, but it was kind of a weird like dad showdown in that sense that like, yeah, no, I can, and I'm standing right next to it, and I know exactly how to do it. I won't, because you could scald somebody, and like you may know that we turned it up, but your kid might not, or you might sell this house or something like that. So that's always a tool that you have, even if there's like some gray area in the code. You will know times that it's like, yeah, this is a tub that should have like a point of use tub mixer like we have that's a higher flow rate, but is still a point of use mixing valve that may be above and beyond what the code requires. But like, and hospitals and elderly care facilities are going to have, you know, their own rules in some jurisdictions, but like, yeah, it's never a bad idea to have more protection than you would think. So.
Yeah, and just a couple of more quick things. And for everybody that's asking any questions and we're not getting to them, we will definitely get back to you. But there's been a lot of them. And like I said, I'm typing like a madman in here. But one of the comments that came through was, you know, is there a way that we can just have just like a quick bullet point list of like why we would do thermostatic over or digital or vice versa? You know, like what are the kind of the pros and cons, right? And Max mentioned that earlier in the download section of GoToWebinar, we do have a PDF that has literally exactly that. And this commenter said basically the idea that, you know, a lot of these building owners, maybe they might want to use the two terrible letters that we all see in this industry, the V and the E, and they think that maybe we can get away with a cheaper valve, right? But I've seen it so many times, you know, when mixing valves, and you guys talked about at the beginning, they're subject to water quality issues, and especially with our electronic mixing valves, and I know there are others out there that do something similar, but both the self-cleaning features or the anti-clog features that we have built into these valves, you know, if you're not dealing with downtime and doing shutdowns at 1 a.m. to do rebuilds on mixing valves, that's worth millions, in my opinion, you know, for a lot of these building owners.
Yeah, that's a good point. Go ahead, Ryan. Did you have something you want to add there?
I was going to say, yeah, definitely, because I mean, even if you do have bad water quality, there's building maintenance guys out there that are carrying extra thermostatic mixing valves just because of that, because they'll take that out, clean it, put in the other one that they have sitting there, and just kind of keep rotating them. And then at that point, if for one building, if you do have 2, 3 high flow mixing valves, you're right there with a digital mixing valve for cost. And then at the time of them taking it apart, cleaning it, switching everything out, you know.
Yep. Yeah. So there's definitely a lot of advantages there. You know, I mean, I know personally, I've seen jobs where, you know, our electronic mixing valve or digital mixing valve has been installed for 5, 6, 7 years without even being touched. And that's so much better than a lot of your thermostatics and even high lows that are going to be out there because they're just so subject to water quality issues. So.
And I think that the value engineering conversation comes up all the time, and I get it that, you know, especially if you're, you know, working for a government project or a school or something like that, nobody wants to overpay for anything. But I think that the scenarios in like a hotel or something that, okay, well, walk me through what would happen if you had to take this thermostatic mixing valve out to clean it. And like you were saying, that if you have another one handy and you're just doing like the magician like switcheroo to put the new one in, that's great. Maybe your downtime is minimal. But if you have to like clean something out and you've got a hotel that's $500 per room per night, and you've got 100 units that are going to be mad about that hot water being down. Like, what is the financial impact of that versus a valve that's going to self-clean? And there's no amount of difference that you could find in our industry that would like cover the cost of that, like impact on a hotel, or not being able to send kids to school because there's no hot water because the replacement didn't go as planned or something like that. I know that there are a lot of people out there. I see that Buddy the plumber on Instagram is one of the. He should be teaching this class. I think he's done this.
He's on today. We could turn on his mic. He's on.
He's done more of these in the like elder care facilities and things like that. That just like, no, he's gonna go in and press in a new digital mixing valve, and it's gonna be the lowest amount of impact there. And I think that that's ideal. So keep that in mind. What would happen if it went down? What's your strategy there? And that like is a much different financial conversation than some number of $200 on the purchase price or something like that. But
right,
yeah.
Right. Well, I think there's lots of great other great questions in here that we had from today, but I think some of them might be a little more involved than what we can dive into here at this point in time. So I think we'll leave the rest of them for getting back to you guys by email. And yeah, anything else to add there, Max, Brian, Matt?
No, thanks to Matt and Ryan for joining us today. They do such a great job on the tech support lines, and we're just kind of moving them into more of a training role as we find spots that we can have them share some of their expertise here. So thanks for doing tech support double duty and helping us out on the training front this week. And thanks to everyone for joining. And we'll see you next month for the Coffee with Caleffi with the IAPMO team to talk about the water demand calculator again. So thanks, everybody.
Yeah, thank you guys.
Thank you, everybody.
Thank you.